Hello students, welcome back to my channel Positron. Dear students, in my last video I have discussed with you all about the capacitor, that what is the capacitor. And I have told you all that I tried to define that capacitor is a device which stores the maximum charge in minimum area, right? Or in minimum volume, you can say. Dear students, I while discussing about the capacitor, I just tried to make an analogy between mechanics, between electricity, between magnetism. How it is? I have said that basically the capacitor is a device which stores the energy in electrical form. In the similar way, inductor is a device which stores the energy in magnetic form, and you know the kinetic energy is in mechanics you write half mv square. This is a linear motion. In rotational motion, how do you write? In rotational motion, your kinetic energy turns out to be half I omega square. M is a mass, V is a velocity here in the case of linear, and here in the case of rotational, I is a moment of inertia and omega is a angular velocity. And you know the stored energy in the capacitor in electric form UE, that is equals to, that is half CV square, and stored energy in inductor in magnetic form, that works out to be half Li square. Now there is a great analogy between these all formulas. It is a linear kinetic energy, it is a rotational kinetic energy, it is a electrical energy in the capacitor, and it is a magnetic form of energy that is stored in the inductor. Dear student, you write K is equal to half mv square. It means what I'm comparing these all formulas in this way. Whatever role is played by the mass in linear motion, same role is played by moment of inertia in rotational motion. And you can say capacitor is actually the electrical mass and inductor is a magnetic mass. You can write it like this. If you will compare it, all these formulas with the half mv square, then it is a mass, it is behaving like electrical mass, and this is behaving like the magnetic mass. Now, dear student, today is a part 2 of the capacitor. We have to talk about, we have to derive the formula for the different capacitors. First, I am going to discuss with you all about the parallel capacitor. Parallel capacitor. Dear students, a parallel plate capacitor, whatever you say. Dear student, while discussing about the capacitor, I have told you all that capacitor is consisting two plates, right? In parallel capacitor, parallel plate capacitor, it is consisting two plates. But at the same moment, I have told you all that actually capacitor is a single plate. You have to devise the method, you have to invent the method that how the maximum charge can be stored on this surface area, right? Now, in order, if here is this single plate, every plate is a capacitor, even you are capacitor, me is a capacitor, we have so many charges in our body. We all are the capacitor, we store the charge, we have so much charge, you know, sodium, potassium, so many ions are there in our body. Everybody, whether living, non-living, no matters, everything is consisting the charge in itself. But capacitor is a differently devised method, differently devised device which stores maximum charge or which stores maximum electrical energy in minimum volume, right? What we used to do during the discussion with you all, I have told you all, actually this this is the capacitor. This single plate is a capacitor. Our motive is to give the maximum charge to this one. But you know there is a limit. If you will give the charge, you know if you give the charge, that potential increases, right? Now it is directly proportional to potential. If you increase the charge, if you give the charge, increases the charge on the capacitor, the potential increases. And ultimately what happens, if you continuously increase the charge, then it will reach to a level of potential that is 3 into 10 to the power 6 volt. This is called breakdown. It means that this plate has, you have given so much charge. Now question is that how much charge a plate or a device or any object can be given, how much charge it can be given. The charge given to a body depends on the potential, right? If you increase the charge slowly, gradually, then its potential increases and ultimately it comes to a level 3 into 10 to the power 6 volt, and this is called to be that the body has come into, you have brought the body into breakdown. Say it fallen into the breakdown. Now you cannot give more charge, because if you give more charge, then the charge will be leaked in the air, right? So now the question is that if there is a single plate, so you charge it and ultimately it has reached to this very level of voltage, means it has it comes into the, it falls into the breakdown. Now you can give, you cannot give it further charge. So how it can, how you can give its more charge? What you have to do, you have to bring down its potential without decreasing the charge. That is why what do, you put another plate here. If you have given this to a positive charge, undoubtedly by the induction a negative charge will be introduced here, right? Because of induction, negative charge will be introduced here, and this side of the plate will become positive. And if you underground it, right, if you ground it, then what happens? Because of ground, these positive charge will vanish. What is means of ground? If there is a positive charge, then ground means negative charge will travel from the earth and will come and neutralize it. And if here is a negative charge, this negative charge will go to the ground itself. What I mean to say that whether there is a positive charge or negative charge, if you ground it, ultimately the charge has to vanish, no matter whether it is a positive charge or negative charge. So dear students, what again I am repeating my words, that actually this is the plate of capacitor, this is the capacitor. Seeing everything in this universe is a capacitor, whether it is a living or non-living body, no matters, everything has its own capacity to store a bit of charge. Dear students, actually this is the plate to which we want to give the maximum charge to its surface, because you know, if you gradually, if you continuously increase the charging, then ultimately it will reach to this level of voltage, and this is said to be that body has come to the breakdown. So now you cannot further charge it. If you will further give it to the charge, then the charge will be leaked in the air. So what we have to increase the charge, but without increasing the potential. Now what we have to, you have to find a technique that you can give it the charge, but the potential should not increase, or you can charge it only when is you can you would be capable of decreasing the potential. Okay, you can charge it further only when you are capable of decreasing its potential without decreasing the charge. What I want to say, what I want to tell you, dear student, I have said that if you are continuously increasing the charge on it, then it will come to a level of this voltage. This is called to be the breakdown voltage. Further, you cannot give the charge to it. If you will give the charge will be leaked in air. So what technique you have to apply, that you have to bring down its voltage without decreasing the charge. Once if you have brought down the voltage, then you can further charge to it. For bringing down the voltage, what I am doing, I have brought a plate, another plate here, right? A neutral plate I have put in front of this one. Then what happens? Now a negative charge will be introduced on it. On this other side, a positive charge will be introduced. Now I have grounded this one. Grounded means if there is a positive charge, then negative charge free electrons from the earth will travel and just neutralize it. And if there is a negative charge, this negative charge will travel to earth itself. It means in both the cases, whether there is a positive charge or negative charge, it has to vanish if it is being grounded. Now, dear student, what is the advantage you have got? Now look here. Here is a positive charge. Already you have given to this very plate, right? I am not going to decrease the charge at all. Without decreasing the charge, I am going to bring down its potential. How? Look here. Here is a negative charge. Because of this negative charge, potential of this will decrease. Because of negative charge, potential is a negative. Because of positive charge, potential is a positive. Because of this negative charge, the potential of this plate decreases, and ultimately you now look here, very interesting. Because of this negative plate, potential of this plate decreases, and other side there is a positive charge, and because of this positive charge, potential of this one decreases. But our ultimate goal is, without decreasing this charge, we have to decrease the potential of this plate. For that purpose, we have brought a plate here. This was neutral plate. Because of induction, this plate becomes negatively charged. Because here is a positive, it will attract the negative charge, and other side will become positive. Now, because of this negative plate, the potential of this plate decreases, and because of this positive plate, potential of this plate increases. But the negative charge is more closer to this positive plate. That is why there will be decrement, greater decrement than the increment, and ultimately its potential decreases. But your goal is to decrease the potential. So if because of this charge, potential of this one is increases, so what we are going to do, we are going to ground it. And if you ground it, the negative charge will travel, the free electrons will travel from the earth and will neutralize this, and so the other surface of the plate will vanish. There will be no charge in it. So because of this, potential was increasing, and because of this, potential was decreasing, and now there is you are left with only choice, that because of this, potential of this plate decreases, and ultimately you have been capable of decreasing the potential. And once you have been capable of decreasing, you are in position to decrease the potential of this capacitor. Now you can charge it further. Now, dear student, look here. I have not decreased, in the whole discussion, I have not decreased the charge on it. What I have tried, I have tried to bring down the potential of this with the help of another plate. This another plate is helpful in decreasing the potential of this very plate, and this is said to be the parallel plate capacitor. Now, dear students, very simple. You know, if there is a single plate, whether it is a positive or negative charge, no matter, close to it at any point, E is equal to sigma upon 2 epsilon naught. But if there are the two plates, one is a positively charged and there is a negatively charged, at a point, if you apply the Gauss law, it comes because of the Gauss law. With the help of Gauss law, you can find out the electric field close to a point, electric field at a point close to a plate, infinite thin sheet, E is equal to sigma upon 2 epsilon naught. Dear student, if point P is here, actually in this case, in this formula one, you should be very clear that E is equal to sigma upon 2 epsilon naught. It is not depending on the position. It means close to the plate, whether this side or this side, no matters, electric field is a uniform. Now, dear students, whether you take a point here or in the mid, no matters. Electric field at any point due to this, at this point, how do you find out the electric field? How do you define the direction of a electric field at a point? Let a point P we have selected here. Now, in order to find out the direction of electric field at point P, what we are going to suppose that let a positive test charge is placed there, and this charge will repel this positive test charge in this way, so it is even, and this negative charge will attract this one in this way. This is E2. You can, so net field E is equal to E1 plus E2. Now, dear student, it is actually sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, and that becomes sigma upon epsilon naught. Sigma is a charge density. Charge will be distributed on the plate, on the surface of the plate. So, sigma is equal to charge per unit area Q upon A, or you might write E is equal to sigma upon epsilon naught. Sigma I am replacing by Q upon A epsilon naught. Now, electric field, how you can define the electric field? Electric field is represented as a negative gradient of potential. If you know the definition, how do you define the field? E is equal to minus dV upon dr, right? Or E is equal to, this is called minus grad V. Electric field is defined as a negative gradient of potential. Gradient, in simple language, you can say that gradient of rate of change of potential with respect to distance. You can say like this. E is equal to minus grad V, or you can write E is equal to minus dV upon dr, or electric field is defined as a negative gradient of potential. Now, dear student, E is equal to Q, sigma I have replaced with Q upon A, right? So, becomes E is equal to Q upon A epsilon naught. Now, dear students, what happens? With this, you can write E is equal to relation between electric field and potential. Let the potential difference between these two is a V. So, E is equal to V upon D. And so, E I am replacing with V upon D, that is Q upon epsilon naught, or Q upon V is equal to epsilon naught upon D. I have brought this to here, V to here. So, Q upon V is equal to this, and Q upon V is actually C. C is equal to epsilon naught upon D. This is the formula for the capacitance of parallel plate capacitor. C is equal to A epsilon naught upon D. What I have done? Again I am repeating that electric field between the two plates, one is a positively charged and there is a negatively charged, is equal to sigma upon epsilon naught, where sigma is the charge per unit area. So, E is equal to sigma upon epsilon naught. Sigma I have replaced with Q upon A, and E is equal to V upon D, relation between electric field and potential in general. But actually, if you want to know actually what happens, E is equal to minus dV upon dr, or minus grad V. Or you can say that electric field is defined as a negative gradient of potential. Dear students, you must be surprised to know that E is a vector quantity, but the potential, electric potential, is a scalar quantity. Now, here is a vector, but here is a scalar. Then how it is equivalent to each other? Dear students, actually it is a gradient is a operator. Gradient is a operator. Operator means positive, negative, division, multiplication, differentiation, integration. All these are the operators. In the same way, gradient is a operator which is applied on a scalar and convert it into the vector. E is equal to minus grad V. V is a scalar, and when gradient operator is applied on the scalar, it turns it into the vector. This is the real thing. Okay, so E is equal to minus grad V. What I mean to say that gradient is a operator which is applied on a scalar quantity and it converts it into the vector quantity. And so that is C is equal to epsilon naught upon D. This is the capacitance of parallel plate capacitor. Now dear student, look here. You got that C is equal to epsilon naught upon D. If a dielectric is filled, right? If the dielectric is filled, dielectric is completely filled and having the dielectric constant K, then capacitance of parallel, you can write this C naught is equal to A epsilon naught upon D. It means it is an air filled capacitor like this. And if a dielectric is filled, then it turn out to be C is equal to epsilon naught K upon D, where K is said to be the dielectric constant for the air. K is equal to 1 and the maximum value is K, of the K is for the water, and that is K is equal to 80. Dear student, one thing is very important. All the dielectrics are insulated. All the dielectrics are insulated. But just I have said that K is equal to 80 maximum for water. It means water is also insulated, right? It means because just we say that dielectric is an insulator. Most of all the dielectrics are the insulator, and for the water K is equal to 80. Dielectric constant of water is maximum, that works out to be the 80. It means water has the maximum dielectric constant. It means water should be insulated. Yes, pure water, I mean rainy water, is an insulator, right? So C is equal to if a dielectric is filled completely, a parallel plate capacitor with completely filled dielectric, that is C is equal to epsilon naught K upon D. This is the parallel plate capacitor. Dear students, what happens? Let's talk about capacitance of sphere, right? This is a sphere having radii r, right? And let charge q is distributed over it, right? This no matters whether it is a hollow or solid, no matters, right? This is a conducting sphere having the radii r and charge q is given to it, right? Now we have to find out the capacitance of the sphere. Just at the beginning of today's lecture, I told you all that everything, everybody, living or non-living, is a capacitor. Capacitor means what? A device which has a capacity to store the charge. But capacitor is a specially devised method to store the maximum charge in minimum area, right? So dear student, everything is a capacitor. Even we are the capacitor. We have so many charge in ourselves, right? We consume so much charges. We have so much charge in our blood. I think there. I do not know much about the geology, but I know the blood is containing sodium, potassium ions, like so, right? Lack of sodium ion can cause the heart attack, cardiac arrest. Okay, let's come back to the topic. Dear student, it is sphere of which capacity we have to find out. Very first thing, you should be very clear that capacitance of an object or capacity of an object is independent of the charge, right? There is no matter. Charge doesn't decide the capacity, but capacity decides that how much charge it can take, right? Your mom makes hundreds of chapatis every day, but it doesn't mean that you eat all the 100, right? Your whole family might eat 100, but you doesn't you doesn't eat 100, right? So there are 100 chapatis, right, in your home, but it doesn't mean that you will eat all that 100. How much you will eat, it depends on your capacity. You might eat 2, 3, 4, 5, right? So similarly with the capacitor, that charge is not going to decide the capacity of the capacitor, but the capacity of the capacitor decides that how much charge it can consume. Now dear student, charge Q is distributed over this sphere. If let it is a hollow sphere, then charge Q will be distributed on the surface. If it is a solid sphere and conducting, even then, wherever you will give charge, let it is a solid sphere and conducting. Even at the center, if you will give the charge, charge will automatically come to the surface. Why it is? We will talk further, right? Now, dear student, you know the potential V is equal to, works out to be 1 upon 4 pi epsilon naught Q upon R, right? If it is a hollow sphere on which charge Q is distributed uniformly over the surface, having the radii, then you know V is equal to 1 upon 4 pi epsilon naught Q upon R, right? Or you can say the behavior of hollow sphere or the spherical shell will be such that whole charge is kept at the center. It is behaving the charge, yet the charge is distributed uniformly over the surface, but it behave like such that whole charge appear to be centered at the center. Why? Look here, the charge distributed in this way, right? Now, the electric line of forces emerges out in this way, right? So it appears that the electric field lines actually begins from here, goes to the infinite, but it appears that these electric fields, yet actually in fact these electric field lines are beginning from here, from the surface of the sphere, but it appears that it is coming from the center. All these field lines appear to come out from the center. That is why you can, the behavior of this charge distributed on the sphere of the on the surface of the sphere appears to kept at the center. So dear students, generally you can say at all these points the potential will be same. You know that you must have studied the equipotential surface above. At all these points the potential will be same, right? Constant. And so V is equal to 1 upon 4 pi epsilon naught Q upon R. There are many spheres. Dear student, what I mean to say, at this sphere, at every point, there will be potential, let it is V1. At this sphere, every point, potential might be V2. At this sphere, every point, potential, let it is V. At this sphere, potential will be same. At this sphere, potential will be same. But at these two spheres, there will be difference of potential, or you can say the potential difference. Now, dear student, V is equal to, if radius R charge Q is distributed, then V is equal to 1 upon 4 pi epsilon naught Q upon R. Now, dear students, look here. You can write Q upon V is equal to 4 pi epsilon naught into R, right? And Q upon V is equal to C is equal to 4 pi epsilon naught into R. Or C is equal to, if a dielectric is filled in the sphere, then C is equal to 4 pi epsilon naught, okay, into R, right? C is equal to 4 pi epsilon naught K into R. Dear student, your Earth is a sphere and having the radius 6400 kilometer. So, radius of the Earth works out to be R is equal to 6400 kilometer, or this is 6400 into 10 raised to the power 3 meter, or this is 6.4 into 10 raised to the power 6 meter. Replace here. Replace the value of 4 pi epsilon naught is a 1 upon 4 pi epsilon naught is a 9 into 10 power 9. So 4 pi epsilon naught is a 1 upon 9 into 10 power 9. Replace the value of R and you can get the capacity of the earth. If you find out actually the capacity of the earth, very important thing what you should know here, what you should be attentive here, you have to take attention of that 1 farad is a very big unit. Even the earth does not have the capacity of 1 farad. That is why we talk about microfarad, picofarad, nanofarad, like so, right? You know, 1 microfarad, I have not told you, dear student, farad is the unit of capacitance, and 1 microfarad works out to be 10 to the power minus 6 farad, and 1 picofarad works out to be 10 to the power minus 12 farad, right? Dear student, what we are talking about that if charge Q is distributed uniformly over a surface, right, then the potential charge Q is distributed on a spherical surface, on a spherical conducting surface, or on a spherical shell, then V works out to be 1 upon 4 pi epsilon naught Q upon R. Right? And so Q upon V is equal to that much, C is equal to this, C is this. What I have told you, that if your earth is a sphere having the radius 6400 kilometer, if you will find out, if you will replace the value of capital radii of the earth, you can find out the capacity of the earth. Even the capacity of earth is not close to the 1 farad. It means farad is a very big unit of capacitance. That is why we used to talk about, normally we talk in terms of picofarad or microfarad. It was the capacitance of the sphere. Let's talk about next is a spherical capacitor. Whether it is a parallel plate capacitor or the spherical capacitor or the cylindrical capacitor, whatever be, right? In order to store the maximum charge or in order to charge maximum to a plate, you need other plate, right? You need 2 plate, right? So, in the case of parallel plate capacitor, there are the 2 parallel plate. One is a positively charged and another one automatically becomes negatively charged because of induction. Same parameter you have to apply here, you have to apply here. Look here. In the case of spherical capacitor, what I am doing, I have considered 2 spheres. The second one is the bigger one. This has the radii A and this has the radii B. Let inner sphere is positively charged. Then because of induction, the other one will be negatively charged and the other side of the bigger sphere will be positively charged. Then what I am doing here, I have grounded the outermost sphere, outermost part of bigger sphere, and so because you grounded, again I am repeating my words that the electrons from the earth will travel to here and will neutralize this positive charge at the outer surface, outer layer of bigger sphere. So it is a positively charged and you are left with negative charge here. It has the radii A and it has the radii B. Dear student, this might be a solid sphere, no matters, but it should be hollow one. right? Now, dear students, and between these two, undoubtedly, obviously, you can feel it with the dielectric, right? Dear students, look here. How will you find out the potential difference of potential? Potential difference simply means difference of potential. Actually, in the physics, there are many quantities which are not the absolute. Absolute quantity, a physical quantity which can be defined independently is said to be the absolute quantity. Like motion. Motion is not an absolute quantity, right? In order to define the motion, you have to consider a frame of reference, right? In similar way, temperature is not absolute quantity. Many quantities are not the absolute quantity. In similar way, your potential is not the absolute quantity. Always we talk about the potential difference. Whenever we talk about potential at a point, it means we are talking about the potential difference at that point and between that point and infinite, because the potential at infinite works out to be zero. You have to very clear that potential is not absolute quantity. You cannot independently define the potential of a point, but always you define the potential difference between the 2 points. If you say that potential at this point, it means you are considering the potential difference between this and infinite, because at the infinite potential works out to be zero. Now, dear students, here is a positively charged sphere. This is the negatively charged sphere. The outer part has been grounded. Let this one has the radii A and this one has the radii B. Then the potential difference will be the net potential. You can say because of positive charge, potential is positive. Because of negative charge, potential is negative. The same I am applying here. Because of this one, potential will be 1 upon 4 pi epsilon naught q upon A. And because of negative charge, potential will be negative, and because of this 1 upon 4 pi epsilon q upon r is a b here. So what I have done, q upon 4 pi epsilon I have taken out. So it works out to be 1 upon a minus 1 upon b. Very simple. AB is a LCM, so it turns out to be minus a. V is equal to this, or you can write Q upon V is equal to 4 pi epsilon naught AB upon B minus A. How it is? Q we have brought here, so this will come to here and this will come to here, so it becomes like this. And Q upon V is what? C. C is equal to 4 pi epsilon naught AB upon B minus A. This is the capacity of spherical capacitor. C is equal to 4 pi epsilon naught AB upon B minus A. In this way, you can find out the capacity of spherical capacitor. Dear students, last one is a cylindrical capacitor. After that is a cylindrical capacitor. It's also very simple, nothing we have to do much. Now we are going to study cylindrical capacitor. Dear student, the same thing I am repeating, the same concept I am repeating, even while solving, even while deriving the capacitance of cylindrical capacitor, the same concept I am applying. First, what do you require? You need to find out the electric field. How do you find out the electric field? Applying Gauss, right? Integral E dot ds is equal to q upon epsilon naught. E dot ds is what? Said to be the electric flux. Like B dot ds is what? Magnetic flux. Flux is a what? Flux of any quantity is a dot product of that quantity with the area vector. So either E dot ds or B dot ds. E dot ds represents the electric flux, whereas B dot ds represents magnetic flux. So in the case of, if you apply the Gauss law for the electric field, then integral E dot ds is equal to q upon epsilon naught. Do you know, later on you will study the Gauss law for the magnetic field, that works out to be b dot ds integral b dot ds is equal to 0, means magnetic flux over a closed loop vanishes. Why it is, we'll talk later. When the topic will come, then I'll discuss with you all. Dear students, next topic is a cylindrical capacitor. Cylindrical capacitor is a what? Very simple. Look here. This is a cylinder, and inside it there is a smaller cylinder, right? Cylinder having, these are coaxial cylinder. Rather you say smaller or bigger cylinder, you say they are the two coaxial cylinders having the same axis, right? The inner one having the radii small a and the outer one having the radii b. It does not matter whether you you give positive charge to this one or negative charge to this one. So what I am doing, giving it positive charge, right, and to this one negative charge. Outer layer becomes positive charge, and if it is grounded, then again the positive charge will vanish. Dear student, it is consisting, the cylindrical capacitor is consisting the two coaxial cylinders, one having the radii small a and another having the radii small b. Inner one is a positively charged, and so because of induction, undoubtedly the inner layer of outer cylinder will be negatively charged, and because outer layer, the bigger cylinder has outer layer grounded, so here, yet by the induction, because of induction, no doubtly it will acquire the positive charge, but this positive charge because of ground will vanish. Ground means whether there is a positive charge or negative charge, no matters in both the case. If it is grounded, then no charge will be left, right? Charge will vanish. If there is a negative charge, automatically it will travel to the ground. If there is a positive charge, then negative charge, free electrons from the ground will travel and neutralize it. Now dear student, if you have to find out the electric field between these two, apply the Gauss law, and if you apply the Gauss law, you get E is equal to lambda upon 2 pi epsilon naught r. This is, I'm not applying here the Gauss law, but if we, yet I have find it, right? I have derived it in a few days back, a month back. I have made a video based on the electric field. So in that case, I am very sure applications of, in the case of applications of Gauss law, I have derived this formula is equal to lambda upon 2 pi epsilon naught r. Let the length of the cylinder is L, and if charge is Q, then lambda is equal to, lambda is a charge per unit length. Actually, here we are considering the charge per unit length, but in the case of plate, we have considered the charge per unit area. In many cases, if the charge is distributed in the volume of the sphere, cylinder, whatever be, then we consider rho, charge per unit volume. So dear students, I am replacing lambda like this is equal to lambda is a q upon 2 pi 2 q upon L, so it is L R. You know V is equal to EdR. I am not applying that. Actually, you know the electric potential is defined as minus E dot dr. This is the from infinite to R. This is the actual formula. V is equal to minus integral infinite to R E dot dr. Why it is? Electric potential at a point is defined as work done in bringing unit positive test charge from infinity to that point is the field. Why it is so? V is equal to minus integral infinite to R E dot dr. Why it is defined? So why the electric potential is defined in terms of this? Why? Simply electric potential is defined as electric potential is at a point within the field is defined as the work done in bringing unit positive test charge from infinity to a point within the field. Electric potential at a point within the field is defined as the work done in bringing unit positive test charge from infinity to that point in the field. So V is equal to minus in integral infinity to R E dot dr. So now dear students, look here, it is from here to here, or A to B, actually A to B is that is Q upon 2 pi epsilon naught L dr over R. Now look here, dear students, I'm not from A to B, right? Actually between this space, in between the space. So I'm expressing the limits will be from A to B. Now look here, V is equal to Q upon 2 pi epsilon naught L I'm taking out. 2 pi epsilon naught L I have taken out. So now look here, ds A to B dr upon R. You know, integral dx upon x, simply, you know, it's a ln x. Ln x natural log x means log x base e. If there is a log x base 10, then that is a general log. So it is a, what happens, q is equal to 2 pi, q upon 2 pi epsilon naught L. This is ln R from A to B. If you apply the limit, you will get ln B minus ln A. Then it is ln B upon A. Or you can write V is equal to Q upon L is again lambda upon 2 pi epsilon naught ln B upon A. No, sorry. Write it Q upon L. Actually what we have to do, we have to find out the value of C capacitance, and that works out to be Q upon V. Otherwise we have written in terms of lambda. E is most generally whenever you apply the Gauss law, you write in terms of density, whether it is a linear charge density or be the surface charge density or be the volume charge density, no matters. Dear students, what I have written here, V is equal to Q upon 2 pi epsilon, not that much. Now you know Q upon V is a C. So I'm writing this one here. Look here, Q upon V is equal to V I have brought here, and 2 pi epsilon naught L bringing here 2 pi epsilon naught L, and this ln B upon A, natural log B upon A here. So this is C. C is equal to 2 pi epsilon naught L over ln B upon A. This is the, dear student, this is the formula for the capacitance of cylindrical capacitor. In this way, you can derive the formula for the capacitance of cylindrical capacitor. I'm sure that you people are following. Dear student, let's talk about the last topic of today. Okay, in next video I will discuss. Okay, otherwise video is going to be too long, and I think that video should be of such a time that it should not be boring to you all. I hope that you people are following my videos. If you think that my videos are going to be beneficial, then I request you all that please share, subscribe, and must put bell icon so that you might be notified about my next video. Thank you. Have a very good night.